Hello viewers, welcome to this next lecture on the NPTEL MOOC course on mathematical portfolio theory. So far we have spent several classes discussing utility functions, and in the context of portfolio theory we looked at how we are looking at the maximization of the expected utility, and then we talked about the non-mean variance analysis, and we have looked at some cases or approaches for non-mean variance analysis, and in the last couple of classes we were focused on talking about the safety first criteria, and we have identified and discussed three different safety first criteria. So, in this class we will now move on to an important step of transiting from the mean variance framework to a non-mean variance framework, and we will talk about a new risk measure, that is what is known as the semi-variance. So, accordingly we start this lecture with a semi-variance analysis. Alright, so we start off with a prelude to it by observing that Markowitz, who actually proposed the mean variance analysis, decided to reformulate the portfolio theory by so the mean variance portfolio theory by taking into account only those returns which were very low, and accordingly he defined a risk measure that he called the semi-variance. So, we start off with the definition of semi-variance. So, this semi-variance is designed to capture the dispersion for all those observations that fall below a certain level or threshold. So, semi-variance by this statement we have said that it tries to capture the dispersion. So, it is designed to capture those dispersion for observations which fall below a certain level. So, earlier when we were talking about the mean variance framework, what we looked at is that we looked at the dispersion about the mean on either side. So, that means those dispersion which are higher valued than the mean and those which are below the mean or the expected return, and accordingly we had defined the risk measure to be the variance which was an indicator of dispersion of all the values. But in case of semi-variance we take a more selective approach, and we do not take those returns which are above this predefined threshold, but rather which are below a certain threshold. So, this is sort of motivated by the fact that you are more interested in penalizing those return instances which follow below a certain minimum level, and not penalize those which are actually higher than that certain level, as was the case in case of the risk measure being the variance. So, accordingly, so this threshold, now that you have talked about this threshold, so let this threshold be denoted by letter H, which is applicable to a range or collection or random variables of likely one period rate of return. So, accordingly, the semi-variance for an asset is defined as follows. So, what you do is that in the semi-variance, what we will do is that we will take R I minus H, that is the return on the asset I, and we take the minimum of R I minus H comma 0, and then we take the square of this and we calculate its expectation, and we define this as the semi-variance. We denote this by, so the variance is sigma I square. So, semi-variance will be sigma I square with 2 bars at the top. So, if you observe carefully, what we have here is that you see here the motivation is, if your R I is less than H, that means it falls below a threshold. So, we take the dispersion R I minus H, and if your R I greater than H, then we do not take the dispersion. So, as accordingly, we only take into account when it follows the dispersion only if it falls below H, and ignore the scenarios when the return is above H, and then we take the, so this is written as the minimum of this square. So, we take the square of the dispersion of this, and then we take the minimum of R I minus H comma 0. So, that means that if R I is less than H, you capture the dispersion R I minus H, but when R I greater than H, the dispersion is taken to be 0, and you take the square of this, just as you had done in case of the variance, and you calculate the expectation of this, because it involves a random variable R I, and I define this expectation to be equal to the semi-variance sigma I square. Alright, so how do we estimate it? So, using historical data, as we had done in case of mean variance and covariance earlier. So, we will give the estimate using the historical data as follows, and this is sigma. So, sigma by square, that is the semi-variance. This, based on historical data, will be given by the expectation. So, it is going to be the average, assuming that all these events are equally likely with probability 1 by t, and summation of minimum of R I t minus H comma 0 square, and this can be written in the form of 1 by t summation small t equal to 1 to capital T of R I t double bar minus H square. And here I have suddenly introduced a notation R I double T bar as R I t double bar, and I have to define this. So, this is defined as R I t if R I t is less than H. So, that means that if your R I t is less than H, then this term will become then R I bar t. So, R I t is R I t double bar is R I t if R I t less than H. So, accordingly, the term that will be minimum is going to be R I t minus H, and so accordingly this becomes R I t double bar H square, and this is going to be simply H if R I t greater than H. So, then this means that R I t double bar minus H will become 0, which corresponds to this value. So, this means that if you look at the historical returns R I t for all time periods, in case your R I t falls below the threshold, you keep them separate and you see that how much is it different from H, and you look at the difference R I t minus H, and in case if it is greater than H, so obviously R I t minus H is going to be equal to 0. So, for each time step you are looking at the minimum of these two and then you square them. So, this is going to give you the minimum of R I minus H comma 0 square for each of those past events for t equal to 1 to capital T, and then you calculate its expectation by taking the average of dividing this by capital T, assuming that each of those returns RIT t equal to 1 to capital T from the past is going to be equally likely. All right. So, now in the continuous case, the analogous definition for the semi-variance of asset I is given by, so sigma I double bar square, this is going to be integral from minus infinity to infinity, minimum of R I minus h comma 0 with respect to f of R I dRi, which is the probability density function, and this can be written as minus infinity to h, that means all those R i's which are less than h, and then the minimum will become simply R I minus h square f of R I into d of R I. All right. So, now I make a few observations. The first observation that I want to make is that the semi-variance is called the lower partial moment Secondly, the semi-variance leads us to the definition of semi-deviation, and this is defined as sigma I double bar. So, which obviously is square root of sigma I double bar square. And thirdly, some obvious choices of the threshold h are the expected return. So, that is one obvious choice. In case you are just worried about no loss, then this could be 0, or it could simply be the risk free rate. So, these are just some common choices, but not necessarily the complete exhaustive list. So, there could be other ways of choosing your age. So, accordingly, based on these three choices, R double bar T is equal to R T less than R F. So, this is going to be a minimum acceptable rates of returns. Then R T double bar is R T is less than E R F or E R, that is worse than expected return, and R T double bar is R T less than 0. So, this is negative return. So, this corresponds to falling below risk free rate, falling below the expected return, and the falling below 0 or earning negative return respectively for the three cases. So, once we have defined what is a semi-variance and equivalently what is a semi-deviation, we now need to start looking at the concepts from the Markowitz mean variance framework in the context of the semi-variance or equivalently the semi-deviation. And so, accordingly, what we start is that we start looking at the most important concept that came from the Markowitz framework, namely the efficient frontier and what are going to be dominant portfolios. So, accordingly, I can make the observation that in the semi-variance framework, the concept of dominant assets on the Markowitz efficient frontier is defined as the following. So, here so the efficient frontier, you would recall that in case of the Markowitz mean variance setup, what is the efficient frontier? The efficient frontier was given by by those portfolios such that for a given level of risk, it is the portfolio that has the highest return, or for a given level of return is the portfolio that has the minimum risk, or simply the portfolio that has the minimum risk. So, now when you are trying to define this in the context of the semi-variance or semi-deviation, then we can analogously extend this concept drawn from this definition of efficient frontier or equivalently from dominant portfolios. So, accordingly, the efficient frontier in this context, I will make the following observation, that it is defined as those assets with minimum risk given by semi-variance or semi-deviation for a given level of expected return or the assets with maximum expected return for a given level of risk given by. So, the given level of risk will be given by again the semi-variance or semi-deviation. So, it is the same definition in the mean as was in the mean variance framework, except that instead of variance and standard deviation, we respectively just change it to semi-variance or semi-deviation. Okay, so graphically the efficient frontier is now going to be something which is on not on the sigma ER plane anymore, but is going to be sigma double bar ER plane, and then the efficient frontier is going to look something like this. So, EF. So, EF is for efficient frontier. All right. So, now what we do is we now examine. So, now in the non-mean variance framework, of course, you have to bring utility function into the picture. So, we now examine this concept in the paradigm of the utility theory. Okay, so in order to do this, let us just look at we will see this in the form of the quadratic utility and do a comparison of what happens in the sigma ER plane and sigma double bar ER plane. So, we start off with first the sigma ER space or the sigma ER plane. So, we consider the following example. So, this is just for illustrative purposes, the quadratic utility. So, here we take the quadratic utility UR to be B of R minus C R square, and I will say that R is less than B over 2C, and we will see why this condition is necessary. So, accordingly, what is going to be the expected utility? The expected utility is simply going to be B of ER minus C of ER square. Now, B of ER remains same in the next line, but what we do is that we use the definition of sigma square to write E of R square. So, remember sigma square in this case is going to be E of R square minus E of R whole square, all right. So, accordingly, I will write this as sigma square plus E of R whole square. So, this can be rearranged at B of ER minus C sigma square minus C of ER whole square. And you see, this is something that depends on ER and sigma square, because B and C are constant. So, this can be written as sum. So, this is, I can call this some function f of sigma and ER. So, here del f. So, the expected utility is sensitivity towards the expected return is going to be B minus twice C E of R. and this is going to be 0. Why is this going to be 0 greater than 0? Because I have chosen your r to be less than b over 2c. So, this will mean that b minus twice c into expected value of r is greater than 0, and the sensitivity of f, remember f is a function of sigma and er. So, the sensitivity of f with respect to sigma from this term, it will turn out to be equal to minus twice c sigma less than 0. So, you see that in this case f is the expected utility, and the expected utility is an increasing function of the expected return. So, this means that as the expected return increases, the expected utility is going to increase, and in the second case you observe that as your sigma increases, does your del f del sigma, this is less than 0. So, that means as your sigma increases, then your expected utility diminishes. That means with an increase in the volatility, your expected utility is diminished. So, this is what you see that is a characteristic of this particular example of quadratic utility when you are using the mean variance framework. Now, let us see how we are going to extend this in case of a quadratic utility for the non-mean variance framework. So, for that purpose the same utility function is not going to work, but we are going to have to modify this utility function in a slightly different way, but it should be such that it is actually it qualifies as a utility function, and subsequently we then look at what is going to be the sensitivity of f with respect to ER and sensitivity of f with respect to your semi deviation, that is sigma double bar. So, for this purpose what we have to do is now we move on to the sigma double bar ER space. We have to define a new utility function E of r, and this I will define as Br minus C into minimum of RT minus H comma 0 square for c greater than 0. Therefore, what is going to be the expected utility of this? This again is going to be B of ER minus C of expectation of minimum of RT minus H comma 0 square. And remember, this by definition is the semi deviation. So, this is going to be B of ER minus C, this is going to be, so there is a square at the top. So, this is actually semi variance sigma double bar square, and I will call this. So, you see that this is a function of ER and sigma double bar. So, I will call this a function G of sigma double bar and ER. So, here what we will have is, so here we will have that the sensitivity of this expected return G, that with respect to E of r is going to be B, which is greater than 0, just as it was the case with the function f, and del G del sigma double bar, that is sensitivity with respect to sigma double bar, is minus twice sigma double bar, and since C is greater than 0, so obviously this is going to be less than 0. So, remember that this is something that you have already also observed in case of sensitivity of f with respect to the semi deviation. Okay, so graphically this is going to look something like this. So, here, so this is the first case, and you look at U of r. What is U of r? U of r is Br minus C r square, and this is my threshold H, and this is going to be my B over twice C. And the graph for the newly defined, so this is more important, for this newly defined quadratic utility, this is going to look something like this, and then it is going to be a straight line. So, here this U of r is simply going to be B of r minus C minimum of RT minus H comma 0 square, and your H will be here, and this part, this is going to be the quadratic segment of the definition, and this is going to be the linear segment. Alright, so now that we have talked about what is the definition of a semi-variance and semi-deviation and looked at it in the paradigm of a quadratic utility function, now let us come to the main context of this course, that is portfolio theory, and let us see how we can actually do a portfolio analysis in this framework of semi-deviation or equivalently semi-variance. So, we start off with this topic now of portfolio analysis using the semi-variance. So, the aim is to determine the set of portfolios that would have minimum semi-variance. So, this is basically determining the efficient frontier in the semi-variance framework. So, it is the minimum semi-variance for a given level of the portfolio's expected return. So, for this purpose we again go back to the drawing board and we recall that the expected return on the portfolio P is given by, and I consider capital N number of assets. So, it is going to be summation I equal to 1 to capital N Wi E of Ri with of course the customary or the statutory constraint that I is equal to 1 to N of Wi is equal to 1. So, now first I need to, so I have said that what I want to do is that I want to minimize the semi-variance for the portfolio for a given level of the portfolio's expected return. So, accordingly the portfolio semi-variance, so far I have defined the semi-variance of an asset. So, now the portfolio's semi-variance is defined as sigma p double bar square, and this obviously is going to be the expected value of minimum of R p minus h comma 0 square, and this is going to be the expected value of minimum. Now, I can replace my R p with this expression. So, this is going to be summation I is equal to 1 to N W I R I minus h comma 0 and the square of the whole thing. Alright, so now this problem is not exactly trivial or straightforward as it was the case in the mean variance framework, and will require numerical computation to ascertain what is going to be the portfolio that will lie on the efficient frontier. So, I will just give a sketch of how the motivation behind this and how it can be accomplished. So, accordingly we observed that several authors have showed that quadratic programming can be used to delineate a convex set of sigma double bar ER efficient portfolios under the following given conditions. So, under certain conditions you can actually get this set efficient portfolios in the sigma double bar ER plane. So, I will enumerate these conditions one by one. So, the first condition is that the variance of returns is finite. The second condition is that the portfolio's semi-variance is continuously differentiable in the weight decision variable that is W I for all I. And the third condition is that the following, so I will list a first order condition. So, the following first order condition is continuous in the weight decision variables that is W I for all I. And what is this condition? This is going to be del of sigma double bar square with respect to W I. This is twice E into minimum of R P minus H comma 0. So, what we need is that we need that the semi-variance should be continuously differentiable with respect to I, and the following first order condition is continuous. So, that means this is continuous. So, typically these three conditions are met or achieved for several well established probability distributions. All right. So, just to make a note that the semi-variance, so semi-variance efficient frontier as we have enumerated now. So, this semi-variance efficient frontier is not driven by the symmetric variance covariance matrix, since, and the reason for this is that this semi-variance defined by Markowitz results in what is known as the co-semi-variance is not symmetric. That is sigma I j double bar and sigma j I double bar, these are not equal for most part. So, now I have abruptly brought about this sigma I j double bar and sigma j I double bar. So, what we have done is, so far we have extended the definition of variance and standard deviation to a semi-variance and a semi-deviation. Now, in the original Markowitz framework, we had this covariance matrix which was symmetric, but the analogous matrix or analogous entities that were part of this matrix, they are not symmetric to each other as per the definition that we are about to present. So, accordingly the Markowitz, so I just want to be more specific about this co-semi-variance. So, the Markowitz co-semi-variance for a finite joint probability distribution. So, there are two variables involved. So, we have to have a finite joint probability distribution is given by the following, and this is sigma I j double bar. This is going to be equal to the expected value of R I minus H into minimum of R I minus H comma 0. And from the empirical point of view, this is estimated as 1 over T summation T is equal to 1 to capital T of R I T minus H into minimum of R J T minus H. So, this is R J T minus H comma 0, and this can be further simplified to 1 by T summation t equal to 1 to capital T r I t minus h into r j t double bar minus h. So, for that you recall the definition of r j t double bar. So, in summary we can say that thus the Markowitz co-semi-variance is the weighted average over all T pairs of RIT and RJT that makes use of only the paired values for which RJT is less than H. Okay, so just an observation that the Markowitz co-semi-variance as we have defined just now may be 0 if the returns of asset I and j are independent of each other. So, this anyway is sort of obvious from the fact that the covariance of two independent random variables is equal to 0, and so this can in turn be visualized or intuitively seen in case of the co-semi-variance. The other way that the co-semi-variance can actually be 0 is that if all the returns of asset j exceed the value of h. So, what this is going to do is then in that case it is going to render this term to be equal to 0 if it is exceeded in all cases. So, also the other observation is that when I equal to j, so let me enumerate this as two separate observations. So, when I equal to j, the co-semi-variance will be equal to the semi-variance, that is sigma I j double bar is going to be equal to sigma I square double bar. Alright, so now what I want to look at is that since we are drawing analogies with whatever we have done in case of the Markowitz framework, that is the mean variance framework, and we started off by talking about the utility functions, and then we talked about the efficient frontier and also made certain observations about the analogous version of the covariances, namely in this case it is called the co-semi-variance. So, one key topic from the mean variance framework that needs to be now examined in the context of semi-variance is what is the capital market line or the capital asset market capital asset pricing model. So, that means you have to start looking at the two aspects that we did when you were talking about the CAPM framework, namely the CML and SML, when the risk measure is no longer the variance or standard deviation, but is instead replaced by the semi-variance or the semi-deviation. So, accordingly we start off with the concept of the capital market theory with the semi-variance. So, this goes back to a paper by Hogan and Warren which came in 1974, and what they did was that they obtained a capital market line in the sigma double bar ER plane instead of the sigma ER plane that is there in case of the mean variance framework. Now, we let this CML be denoted or named as CML of SV, just for semi-variance. All right, and this CML, the formula is given by the following. So, here we will have, as before, we will have E of Rp is equal to Rf plus ERM minus Rf over sigma m into sigma p, which was the original CML, and in this case the only change that will happen is sigma m will be replaced by sigma m double bar and sigma p will be replaced by sigma p double bar. The interpretation is that this is an equilibrium portfolio pricing model, where the expected return from an efficient portfolio P, that means E of Rp, this is equal to the risk free rate plus the risk premium which is given by this term. Graphically, let us have a look at how this is going to look like. So, here we are in the sigma double bar ER plane, and so I start off with RF, and this point of tangency as before is the market portfolio. So, this will give me the corresponding E of RM and sigma m double bar, and this curve here is EF for efficient frontier, and this line which is what is known as the CML in the semi-variance framework. So, this is nothing but the CML in the semi-variance framework in the sigma double bar ER space. So, now we come to the last topic, that is the SML in the semi-variance framework. So, the SML for an asset I in the paradigm of the semi-variance analysis, which is denoted by CML SV, is given by E of Ri is equal to Rf plus E of Rm minus Rf into beta I. So, remember that this was the original SML. So, again the only thing that changes in the context of semi-variance is that the beta I is replaced by beta I double bar. Now, I have introduced what is beta I double bar. So, I have to define that beta I double bar, this is going to be sigma I m double bar over sigma m square double bar, and the numerator according to the definition is going to be the expected value of Ri minus h into minimum of Rm minus h comma 0, and the denominator is simply going to be the definition of semi-variance for the market portfolio, which is expected value of minimum of Rm minus h comma 0 whole square, and this can be reduced to E of Ri minus h into Rm double bar minus h over E of Rm double bar minus h square. And this beta which has been newly introduced, that is beta I double bar, this is called the downside beta. The reason why we use the term downside beta here is that because it captures the sensitivity of the asset with respect to the market portfolio in the context of the downside risk, that means the risks associated from the losses driven by the returns falling below a certain threshold level. So, further what we can write is that this relation that we had E of R I is equal to R F, this SML, this R F plus E R M minus R F into beta I double prime. This relation that we have derived here, this is referred to as the downside SML or as the downside CAPM. Remember, CAPM is synonymous with SML. So, graphically this is what it is going to look like. So, I will have to consider this in the beta double prime double bar plane against E of R, and this SML, which I will denote it as SML. So, here please make a correction, this should be SML SV. So, here this SML SV, this is the line which emanates from RF and this passes through M. So, I get the corresponding E of RM, and here I get beta M double prime. So, this graph is nothing but this SML SV or the SML for the semi-variance framework in the beta double bar ER space. All right. So, this brings us to the end of this lecture. Just to do a recap, we have mainly focused on this lecture in dealing with various aspects of semi-variance or equivalently semi-deviation. Semi-variance is designed to capture only those returns that follow below a certain threshold, and the standard deviation of that or the square root of that is what is the standard deviation equivalent, namely it is called the semi-deviation. And then we looked at this from three perspectives, this entire discussion. And what we had looked at here is we first looked at from the point of view of the utility and the expected utility, then we also talked about the efficient frontier, and finally, we also included and discussed the extension of the capital market line and the security market line in the context of making the transformation from the mean variance framework and getting the equivalent CML and SML in case of the semi-variance or semi-deviation framework. In the next class, we will continue our discussion on this non-mean variance theory, and we will introduce a new topic which is called the stochastic dominance. Thank you for watching.